Thank you so much, sir. Well, as all the participants stay here. आपण तिकडे जाऊ थोडंसं लेक्चर मला Pradeep sir, we have made you a co-host so that you can share your slide. I just introduce you and then you can start.
Hello.
Yeah. Sir, am I audible?
No, you are audible, but very faint, very faintly. But I don't know if you, I'm audible to all of you.
Yes, sir. You are audible to us.
Now it's better.
Yeah. So, dear participants, let us welcome the speaker of this second session for day 1, Mr. Pradeep Goyal, fellow ASM. He was president of ASM International for year 2023-24. Mr. Pradeep Goyal is chairman and managing director of Pradeep Metals Limited, Mumbai. Mr. Goyal grew up in Mumbai and completed his BTech in metallurgical engineering at IIT Kanpur in year 1978, graduating with the first rank. He was awarded a silver medal by the President of India. IIM awarded him the best metallurgist of the year. He completed his master's in metallurgy at MIT in 1980 with a research assistantship. After 3 years at Air Products and Chemicals INC, he returned back to India in 1983 to start his own company, Pradeep Metals Limited. He is the chairman and managing director at Pradeep Metals. Mr. Goyal has served ASM International as chair of India chapter from 2002 to 2005 and trustee of ASM International from 2005 to 2008. He was recognized as fellow ASM in 2015, fellow of Alpha Sigma MU in 2017, and awarded distinguished life membership in 2021. Mr. Goyal has organized and chaired 5 major material science events and helped the India chapter build an office and training center in Mumbai. He serves on the boards of many corporations, including UPL Limited, the 4th largest agrochemical company in the world. He is a member of the Technology Development Board of India, member of the board of Indian Institute of Technology, Kanpur, IIT Bombay Research Park, and National Institute of Advanced Manufacturing Technologies. Mr. Goyal is conducting research on a novel manufacturing process on which we are going to hear from him. That process to manufacture steel using microwaves, and holds several patents for this process development work using microwaves. He has served as the past president of Rotary Club of Mumbai South and past assistant governor of Rotary International District 3141. He is currently the chair of Ekal Abhiyan Trust, an NGO that runs over 80,000 single teacher schools in the remote tribal areas of India, providing primary education to 2.2 million children up to the 3rd grade. I think his biodata is more and time is limited to introduce you, sir. So I hand over you this session and request you to please start your session.
Can you make me the host so I can share my slides? Thank you very much for this introduction.
We have made you co-host. You can share your slide.
Okay. Can you see my presentation or no? Hello?
Most of
Sir, now you do it.
Slide
No,
is
sir.
not, slide is not visible, sir.
Now you do it.
Hmm.
host कर निखिल host ना पूरा host कर
I am the host, but I am trying to open it from my desktop.
Sir, just share your screen.
Yeah, I'm trying to do that.
What happens? There is a button, share. Yeah.
Is that
Yes,
okay?
sir. Perfect. Perfect.
Okay.
Just do, yes, sir.
Okay. Is that good?
Yes, sir.
yes sir perfect
All right. Wonderful. All right. Ladies and gentlemen, thank you so much for inviting me to give this little talk on microwave research that we are doing at our company. Uh, Basically, our company has nothing to do with microwaves. We are in the business of making forgings and exporting them. But this came as a sort of offshoot of what I wanted to do based on some of the work that I had done in the past in research. So I'll just go through some of the work that we have done in this company since 2006. That's when we started this microwave activity. And this research has been going on for past so many years. Several processes have been developed. It's a very challenging environment to work with microwaves. As you all probably understand and know, each one of you knows what a microwave is, for sure. I think there is no home which does not have a microwave cooking arrangement in their kitchen. But we always fear that we cannot put metal into the microwave oven. Everybody warns you, do not put a spoon, do not put any metallic components in the microwave. That's correct. What happens basically is that I'm just giving you a little background so that you understand where I'm coming from. When you put a metal in a microwave, the basis on which the microwave works is that the equipment has a microwave generator. That generator converts electricity into microwaves at a particular frequency. And those microwaves are used for heating your food. What heats your food? Your food is heated because of the water molecule that is there in the food. If there was no water in the food that you have, nothing will happen. You will not be able to heat the material inside the microwave. So anything that needs to be heated in a microwave must have a method to couple with the microwave. And by that, I mean that the molecules of that material must vibrate under the microwave conditions. Okay, so there are many such materials in the world that will couple with a microwave, and you have to identify those. Okay, so the microwave now, just to give you a comparison, you have a regular cooking oven in the at home where you heat the oven, the whole oven gets heated, and with that heat, whatever you keep in that oven, that will get heated by the process of conduction, convection, and radiation from the source of heat. Okay. So the amount of energy that goes to heat your material or food or whatever is very small compared to the energy that is wasted in heating the oven by itself, right? So this is called outside in heating. So outside sources will heat first, and that will heat the material that you have kept inside, maybe a cake or whatever you want to heat. The opposite happens in a microwave oven. When you heat something in a microwave oven, when you open the door, you don't find heat in the cavity in which your food was lying. That's cold. Only thing that has heated is the food that you have kept in. And the plate gets heated by conduction from the food and not the other way around. Okay. So this is called volumetric heating, inside out heating. This is the primary difference between heating anything in a conventional furnace and in a microwave furnace. So now I'm transferring the microwave oven to call it a microwave furnace. And as I go along, you will understand what I mean by a microwave furnace, because you will see the sizes differ significantly from what you have in your kitchen. Although I must acknowledge that the first microwave equipment that we started with was the kitchen microwave to do some trial samples with few grams of material and all those things. Eventually, we graduated to higher sizes of equipment. So with that brief background on microwave heating, I will proceed to what we have. This is just a picture of our factory in Navi Mumbai, which is mainly focused on manufacturing steel, alloy steel, stainless steel, and other forgings, which we typically export. So we started this company, as the introducer has already said, that in 1982, when I returned back from the US. And we have grown with that time. And most of our products are exported to North America, Europe, Japan, China, and all those countries. This is a slightly dated thing. The turnover in 22, 23, 24 was 260 crores. So little growth. Of course, this was the COVID period where you have this number. So we created what is called the Industrial Microwave Research Center in the year 2005. And this is a DSIR, Government of India approved lab. And we conduct research in this lab to exploit innovations in the microwave materials processing. So basically our goal is that we look at processes that can lend themselves to using microwaves rather than the regular conventional furnaces for heating or for any other processes, and to convert these potential applications to commercially viable, energy efficient. So as you'll realize that if you are heating something in a regular furnace, which is gas heated or something, you are actually using fuel. In this case, it's called green because we are using electricity, and soon a lot of electricity is going to be green because of solar and wind and other technologies. So microwave processing is termed as a green process, basically. So we have a variety of different sizes of furnaces available in our factory, in the research lab. The first one that you see here is the one that we brought. It's a 3 kilowatt low temperature baking furnace. We have pilot scale microwave system. We have mineral comminution systems, ball mills, mixers, magnetizers, and susceptibility measuring system. Now, susceptibility is what I talked about, the way any material behaves under the microwave environment, how susceptible it is to absorbing microwaves. That is the intention behind this. Okay. Then we have continuous microwave furnaces. You saw some pictures of stationary batch furnaces. Now you see some continuous furnaces. The one that you see at the bottom is the latest one that we have installed, and I will come to the details of that a little later. and you can put a lot of different microwave powers in it. And to just put into perspective, the kitchen microwave oven is 0.7 kilowatt, generally in that kind of a range. And most of these that we have are 3 kilowatt and above. So it's an order of magnitude higher in terms of the energy that we can, microwave energy that we can provide. All of these are PLC based. We have pyrometers to measure temperatures of the product which is inside the furnace. So we, over the years, have applied for several patents and several have been granted to us. We worked in a variety of fields, in petroleum, in iron ore, processing of grinding wheels, making friction pads for automotive and even aircraft, uh, processing of ores of different kinds. And of course, the biggest one was the iron making technology, how to make iron using a microwave composite heating furnace. And this technology we developed along with the Chubu University in Japan. Initial trials were conducted with a lot of different high temperature works. We did sintering of ceramic plates for solid oxide fuel cell, electrode materials, metallic and ceramic composites, sintering of powder metal base components made of stainless steel, transparent ceramics. So all of these are things that we made a lot of experimentation, but we realized sooner or later that many of these may not convert into commercially viable processes. It was a great learning experience for us, but we did do a lot of different kinds of products that we tried to process in these furnaces. Sintering of porous ceramic filters is a extremely viable process. A lot of Japanese, Chinese mills are using this for casting, and so it's a standard process now. Smelting reduction of iron ore is what I'm going to kind of show you a little more. Purification of lead recovered from scrap lead batteries we did for a company that has developed a low temperature lead recovery process by electrolysis. So some of these works that we did for many different companies. So what are the low temperature processes that we did? Baking of friction pads, rapid curing of grinding wheels, rapid curing of concrete paver blocks, activated carbon from coconut shells, pre-treatment of coal for improving grindability, yield enhancement of heavy vacuum gas oil for petrochemical plant, and disinfestation of food grains. Now, suddenly you will find that, we are moving from industrial processes to a food industry process. And it's a very interesting thing. I will come to that also as we go later. So it's just a summary of what ideas we had done. Presently, the processes that we are focusing on is to scale up the rapid curing of grinding wheels, microwave assisted smelting reduction of iron ore, in hydrogen condition now. We tried pure electric activity, and now we are trying to look into the use of hydrogen. That's the future where the world is headed. Ferroalloy synthesis with microwaves, and finally disinfestation of food grains, rice and wheat, which is becoming quite critical now. So these are our earlier experimentation. You will see very clearly, if you look at the graphs underneath there, the pink graph shows you how fast we can do a certain process under microwave conditions to have a binder burnout compared to the conventional binder burnout process. You could see clearly that we could do it more at a lower temperature, at about 900 degrees instead of 1000, and instead of 16 hours, we were able to do it in about 6.5 hours. So that's a huge amount of energy saving if you see that. So not only are we saving precious fuel, but we are doing it under electric conditions, and the energy consumption is considerably lower. Same thing if you'll see sintering, you'll see the same process, that it happens very rapidly. It's a great process for expediting whatever you want to do, achieve high temperatures. So you can see that within like 4 hours, we have achieved 1200 degrees Celsius in a microwave oven, which many people at some point in time never thought is possible, because when you cook food, you have learned only cooking. It happens at 100 degrees or maybe 150 or some similar temperatures. But here we are going up to 1200, 1400 degrees Celsius. One challenging assignment came to us from DMRL in Hyderabad, that they had tungsten powder and they wanted to actually melt it also in some places. So, and they also gave us the powder to look at how we can make a microstructure better. And here you can clearly see that when we did as received tungsten at 1000x, you see the SEM images of the sintered in microwave at 1800 degrees Celsius with 1 hour soaking. So not only we could go up in steel 1400, but for tungsten we went up to 1800 degrees Celsius in a microwave environment. So there's a lot of porosity as compared to the milled tungsten. And milled tungsten showed a very good microstructure at 1000x. I'm not going to spend more time on this. This is just to give you an idea of the variety of things that were done for our learning process. This was our really a big project that we took up to see that we can rapidly cure grinding wheels. Grinding wheels are used all over in every industry that you can think of. They are used for cutting steel, they're all kinds of things. Now here you see this graph. The conventional is the blue one. So the grinding wheel is so thin, it's like 2 or 3 millimeters. And if you try to heat it very fast, it will crack. The green grinding wheel will crack. So that is why if you see the stepwise process going from 80 degrees to 120 to 150 to 180, and slowly you keep heating this grinding wheel, keep it at a temperature, and after about 1600 minutes, you have baked the grinding wheel. But when we did it in a microwave environment, look at the black graph. We went up rapidly from room temperature up to about 230 degrees and cooled it. And nothing happened. It didn't crack. Nothing happened to the product. Now, if you look at the energy as an area under the curve, look at the amount of energy used here compared to the energy used in under the blue graph. It's huge. So when one time somebody had said that you can save 95% energy by processing materials in a microwave environment, I couldn't believe it. But after doing this research, I could clearly believe that a huge amount of energy is being wasted presently, and that can be saved significantly. So here there's some, you can see some of the performance parameters here for commercial wheels and the microwave processed wheels. You have a much higher properties. We have much higher grindability ratios. So we could actually use this grinding wheel to cut twice the amount of steel compared to the commercially available grinding wheels. So this was a huge success that we are now working towards, full-scale commercialization of this process. So it's very simple, affordable, and economical. Grinding wheel is rapidly and selectively heated by microwaves. It leads to huge reduction in processing time. The process is highly energy efficient, as I said, and the process provides better properties of the product, such as metal removing rate and the grindability ratio. Then we looked at for a oil processing company, the process for pre-treatment of heavy petrobottom stocks. When we make petroleum in the refineries, you get what is called the HVGO, which is then processed in hydrocracking for fractional distillation. We developed a process where we passed the oil through a magnetic condition and we processed it in microwave. And because of that treatment and the exposure, we were able to draw out more kerosene and more fuel compared to what they were actually achieving. And at the same time, we were able to reduce sulfur, which is very important from kerosene and from diesel. So you see the sulfur in diesel went down from almost 18 to 9, half. which was very exciting for these companies. But of course, as the oil companies are, they are giants, and we are a kind of pygmy. So they kind of probably took it up on themselves to carry on further research. So they probably used us to get this data and get this idea. But then they must have, because it's a very large, scaling up an oil company's process is a huge challenge for a small company like us. So we are happy that they were able to, they would probably have looked into this process to get a little more. We found that you could get at least 1 or 2% more fuel, which is huge in a refinery. To get 1 or 2% excess fuel out of the petroleum base is extremely high, very, very interesting for them. Then we took another process, which is the pre-treatment of coal. Now, coal comes in a variety of different types. Some of them are very hard coals, and those coals are difficult to process, and they have trapped water into it. So what that does is that it eats away the energy. The water has to be heated, and it eats away the energy in heating the water. So, and water is what we want in a microwave process, right? So water is what really works. So when we process the coal in the microwave, we were able to take away all the water from the coal. But at the same time, an interesting thing happened, that because of the disproportionate heating of coal and water, the whole coal cracked into, you can see how the cracks appeared. Now this hard coal, which was very difficult to grind, became very pliable for grinding also. So we achieved two successes here. One, removal of water, and two, make it more grindable, easily grindable. And the third benefit we got was that the ash fusion temperature increased from 1160 to 1310, which is extremely crucial for a power plant. When you heat coal in a power plant, that ash that comes out of the coal goes and chokes up your tubes. And so, but if the ash fusion temperature increases, then these ashes will not stay in the tubes, they will go out of there. So the tubes will last longer. So that is another big advantage that came, which we were not really expecting. So that was a unusual thing that we realized. So many times what we find is we do process these things, but we don't understand the underlying technology, what is happening there. So in many ways, we call microwave processing like, you can call it a magic. Many of these things are still not scientific processes. They are processes that have been developed, but the science behind it has still a long way to go to understand some of these things. Now, let me come to the main portion that I was asked to speak on, was the microwave assisted iron making. Right? So we started with very small green pellets to melt in the microwave oven. So we took these green pellets of high-grade iron ore mixed with coal. Now, mind you, in fact, all steel mills use coke for melting, for reducing the iron ore. But we never used coke. We always used coal. And because coke is very difficult and very expensive. And we used some binder, and we were able to melt the pellet very comfortably to get iron and slag. So this is the configuration and the analysis of the iron that we were able to produce in a small scale furnace initially, and with low sulfur, low phosphorus, decent amount of manganese, and 97.78% of iron, which is quite good, and we recovered the carbon. So we were able to make very good quality pig iron. Then we took a higher size. We took a 700-gram green pellet. Now we took the low-grade Goa iron ore. Here the iron content primarily in the ore is only 46%. So a lot of it is sand and other materials. And we did the same process. And here we were able to melt the iron at 1300 degrees Celsius, which is very low compared to what normally the iron is made. And here, if you see the bottom with the pig iron, you see a very small amount of pig iron there, but a very large amount of slag. Okay, this slag is because there was very low quantity of iron available in the raw material that we processed. Okay, and it separated very nicely. You can clearly kind of break off the slag and remove the metal out of that, right? So here you'll see again we recovered all the carbon. Phosphorus was a little higher because the content in the Go iron ore was significantly higher, and of course we were able to recover a lot. Here you see a lot of silica. SiO2 is about 37%. Okay. This was very interesting. This was again a find which was unknown. This was a green glass. So we didn't know what this looked like. So we sent it to a government lab called CGCRI, Central Grass Research Institute. And they were very surprised. They said, "How did you make this?" I said, "We didn't make it. It happened by chance." Okay. So when we were processing this low grade Goa iron ore, we by accident developed this green glass, which they said is very interesting, and maybe the army might be able to use this glass for certain applications. So many times things happen that you don't know, but it was very interesting for us to do that. Again, clean energy source, reduced CO2, SO2, because we are using here only stoichiometric amount of carbon in the form of coal. We don't normally, people use double the amount of carbon because some of it goes to heating the material and some of it goes for reduction. Here we don't need anything, no carbon is required for heating, only required for reduction. So theoretically, we can do away with 50% carbon compared to the regular iron making processes. And we can use fine iron ore and coal powder, which is the cheapest available. None of the other iron making processes can use fines of iron ore and coal, which we can use very conveniently by making pellets out of them. And we don't need coke, sorry. So this is our furnace that we built along with the Japanese for melting of or reduction of iron ore at our plant. So this is installed at our factory here. So here I'll show you the progress, how the smelting reduction reaction takes place. So we put pellets into this crucible. At 1200 degrees, you'll see some pellets. At 1350, you'll start seeing some fused pellets. And at 1425, you'll see a full molten mass. It was very interesting for us to kind of go through this whole thing, which you can also see how this process really occurred. In the background, you can hear our hammer making forgings. So that was just the melting part of it that you saw. But then we took a chance to see how can we pour this liquid metal. You know, you just melting, of course, you can do that. But now we want to really simulate how we would do it in the live environment where you keep on melting and you keep on pouring this metal. So we created this whole infrastructure so that we could tap the molten iron into a crucible outside the furnace. So this is something that we experimented for the first time, and we were so fortunate that it kind of happened. It was really the aha moment for our team who was working on this process, that we were able to tap liquid iron from a microwave furnace. So these are the typical pig iron chemical compositions. You get steel grade pig iron, you have foundry grade pig iron, but then you have three types of pig irons that were made using microwave. One is the high purity iron ore, which all the large companies use to make iron. And here we were able to get this composition compared to what they do. The first two are the what we get from commercial grade of pig iron. And here you'll see that then we took the low purity Go iron ore, and this is the chemical composition of that. We tried another experiment with Nagaland iron ore, which is magnetite iron ore, which nobody uses in the world. We decided that we will try to melt that also and reduce that in our microwave. And we were really shocked and surprised that we were able to process it very low carbon. You can clearly see that this is almost akin to a steel chemistry, just a little bit of removal of carbon. And then we also recovered chromium, nickel, and cobalt, which were there in this magnetite ore, which was a surprise find, which we were able to achieve by Nagaland iron ore. This became of a big interest to the steel ministry because there is millions of tons of this ore lying in Nagaland area, which is magnetite in nature, and no steel mill is willing to use them. So these are some of the results that we see which were out of our knowledge that we would be able to achieve these kinds of results. So again, low carbon consumption, 200 kg per ton of hot metal. It's a direct reduction. Low level of phosphorus, which is favorable. No need to procure hot metal slag as necessary in some other processes. Easier recovery of furnace from a cold condition. 50% reduction in greenhouse gas. Powdery raw materials used without usage of coke. And very fast rates of reaction leading to high productivity. Now, if you look at the conventional process of making iron, you see on the left in the yellow portion, you have a blast furnace. And if you look at the chemistry on top there, you have 6 times the CO, 6 molecules of CO2 produced in the process. While if you look at the microwave processing, by using microwave energy, we produce only 3 molecules of CO2. So this is what I was talking about, that we have 50% reduction in CO2 production. And look at the clean process that we have. We have iron ore fines, we have flux, we have coal fines, we make pellets, and we directly reduce it in a microwave furnace to produce pig iron. While in the other process, you have to take the coal, make it into coke, you have to have coal injection into the blast furnace, you have raw iron ore, you have pellets, you have sinters, put it in the blast furnace, and then you make pig iron. So there's a huge reduction in the number of steps in making pig iron by this process. Why new technology is required? Of course, steel, as we all know, accounts for 7 to 11% of greenhouse gas emissions worldwide. So everybody is looking at ways by which the CO2 reduction can happen. This is the largest commodity produced in the world, in a few billion tons. So any process improvement here would make a huge impact on the CO2. So if we are taking up the challenge to reduce global warming, then steel industry would have to play a large role in that. So here are some of the, there's a shortage of time. I'm going to quickly run that there are many, many companies worldwide who are spending millions of dollars on developing hydrogen green steel and others. Of course, we don't have that kind of money. I wish we had. I'm sure we could have scaled up our process significantly. But these companies are doing a lot of different developments in hydrogen and other steels. Boston Metal has developed a completely different process where they are going to reduce liquid iron into pools at the bottom of a cell, which is mostly like an electrolytic process. High quality steel using less energy and fewer steps. A commercial scale demonstration is expected shortly. So many companies, we are keeping a track of what's happening there. Now we come from 1800, 1400, 1500 degrees Celsius down to 60 degrees Celsius. Okay, why this interest in disinfestation of food grains? I'll come to that shortly. Now in India or worldwide, there are a lot of losses of grain because of insects. Okay, and the nutrition value also drops in that case. So that is why these insects are killed by toxic chemicals like methyl bromide, etc., which are technically banned by the World Health Organization. But due to lack of any other available process, that continues to happen with methyl bromide. So we decided that grain also has water in it, and so does the insect. Insect is ultimately, bulk of it is water. So we decided, let's try this process to kill the insects by microwave processing. So conventional fumigation needs longer duration and it kills only the adult insects. That's very, very crucial here. Most of these chemicals are poisonous and pose health hazards. Conventional processes don't control the moisture content. It's essential to maintain moisture to reduce weevil problems. Weevil is the insect. Sun drying is a very slow process. Low temperature treatments are cumbersome. Atmosphere process control is slow and results adversely due to anaerobic respiration in grain. Now, microwave kills all stages of the insect. So you have egg, larva, pupa, and the live insect. Now, methyl bromide kills only the live insect. The early three stages are not touched. So after 15 days, the pupa comes in and becomes a live insect. So it's a never-ending process. Okay, the microwave kills all the stages. So once you have microwave processed the rice, the all stages are gone, and if you close it at that time and don't allow cross contamination from the air, then the rice is permanently rid of all the insects. And you need a very short time exposure for elimination of these insects. No hazardous side effects on the stored products, very high energy efficiency. It preserves the integrity of the product. And by the way, all of these things have been tested by the government lab from Ludhiana, which is the Post-Harvest Institute of the Government of India. And it complies with international environment rules. So this can be adopted at any stage. It can be immediately after milling, polishing, at bulk storage, but before final packing, or at the port prior to shipping. Depends where you want to do it. So this is the furnace I was showing you early on in the presentation, is what we built for processing of rice. And this is a continuous process where the length is 3 meters. It's a 80 centimeter width zone. Microwave input is 4.5 kilowatts. It's PLC controlled. So this is the process. You have a mixer, you add some moisture to the rice, you have a feeder, and that feeder, then you have a microwave exposure in this portion, and then aspirator for insects. So at the end of it, all the dead insects will get pulled in, sucked out through this thing, and we get only the clean rice at the bottom. So all this rogue collection happens here in this vessel. This is the microwave portion where it's being treated with the microwave. So that rice is now completely devoid of any insect. And if you pack it right away, there is no chance of any insects coming in. So this is the people from the Post-Harvest Institute and our scientists trying to measure, one second, the properties and temperature and other parameters. Of course, this is wheat here. Any grain can be processed in this environment. It took us about a year and a half to completely convince the institute that our process is robust and it can do the job. So they did all kinds of tests, not only at our lab, but also by taking it to their labs to do nutritional studies and all other things that they wanted to study before they gave us a clean chit that we can use this process. Now the challenge is to kind of scale it up, because what we have is about 150 kg per hour of processing, but the demand is to make 10 tons per hour. So it's a huge change that is required, many orders of magnitude higher. But we are in the process of discussing with manufacturers of equipment as to how we can do that. So this is our finding from this whole institute, from this study with along with ICAR. It's 100% insect mortality is observed in this non-chemical management strategy, lower exposure time, maximum of 70 seconds, prototype available for demo with standardized process protocol. So for many decades now, a lot of work has been done in terms of microwave processing of different products, and most of them are by small industrial microwave companies along with users. So much of the technology that has developed is not freely available, and the wheel repeatedly is reinvented over and over again. So that is why people don't share knowledge, and that's why the industry hasn't picked up in a very large way. Except now in many countries, all the chips are made by this. The meat is processed in microwaves, and many of those have become standard processes. So, but not much into the high temperature realm. So, what are the barriers here? The price of the equipment, the risk of failure. Some of the benefits are not understood. Like I said, the science behind is not understood. The lack of technology of using microwaves. People are afraid that if my hand goes into the microwave oven, it will get burnt. Of course, it will, because that's moisture in there. So you have to be careful as to that there is no leakage of microwave from any of your furnaces. And the priorities don't seem to be in the radar of any bigger companies. And every material has different microwave heating properties. Furnaces need special designs every time, and you have need a long time experience of this field. And the microwave generators and devices have to meet the high requirement of industrial production, and stabilized long life power is required. So, and people expect very low prices. That's the whole big thing. So now it's well accepted for cooking. A lesson learned that in this is that industrial microwave heating, the industry must understand the benefits and limitations of microwave. And just simply exposing samples to microwave, you cannot achieve results. So it's not as easy as it kind of appears, but you have to be extremely careful what you are doing and take measurements for effective process control. So all these types of challenges are there. Chemical properties of material need to be understood. Applicator designs are to be developed, and process economics has to be proven. So you can't just blindly apply microwaves. You can be disappointed seriously. But if you use it wisely, you can have really great advantages, particularly like I showed you about rice. Also, the grinding wheel process, extremely high energy efficient process that we developed. So this is our research lab in our factory. Anybody who's interested to actually see what's going on is most welcome. We don't try to hide anything from anyone. Anybody is welcome to our factory in Navi Mumbai, and you can see some of these things happening there. So that's all I had. I think I've just about done it in the time allotted to me. I'm still available for any questions, answers, whatever anybody may have. Thank you very much for inviting me to this event.
Thank you very much, sir, for your thoughtful and wonderful session. Any questions, dear participants? You can either raise the hands or directly unmute and ask the questions.
Namaskar, sir.
Yes.
Is there any change in nutrition value of grains, that is wheat or rice, when you are going to use microwave?
Sorry, I couldn't understand. What was that?
Is there any change in nutrition value of
No.
rice?
I mentioned that the ICAR Institute actually did those studies. We developed the process. They took, you see that person who was there showing the temperature, that's from ICAR. He is a scientist from there. He took all samples of different processing times and different processing parameters, took all those samples, did all the nutritional studies, and they said that absolutely no change in nutritional value. And that is why they have given us the certificate of uh, a clean process for killing these insects without using any chemicals, toxic chemicals. They are cancerous chemicals, actually, methyl bromide, etc.
Thank you very much, sir.
Anybody else wish to ask questions? Meanwhile, I ask all the participants to please switch on their videos so that we can have a screenshot.
Some questions in the chat box, I think.
Okay, yeah.
Can you read them all?
So there is a question from Mr. Amjad Khan Pathan. Can we use same technique for milk or honey?
See, I think the process of honey is a very, very critical material, product. And I think microwave might kill some of the properties of honey. We haven't done any studies, but whatever I know of honey, heating honey is really not advised at any point in time. So heating honey kills a lot of its properties. So I would not recommend heating honey. As far as milk is concerned, I think pasteurization of milk can be done, but it's really not required because the process of pasteurizing milk is so standard now that you may not see a lot of benefit by using microwave.
Sir, good evening, sir.
Yeah.
Sir, my question is, does this microwave heating of metals have any effect, or does it affect the final microstructure of the metal as compared to the when we go for the conventional heating of metals?
See, the speed at which you process, I can mention you, this is the latest thing that we have done is to do heat treatment of steel products. I told you we make forgings and we have to heat treat those forgings. So we actually experimented with heat treating our forgings and we found that the microstructure was extremely fine because there is no grain growth. The process is so fast that you don't see any grain growth, and we got fantastic microstructure, and the speed, the time that was required for heat treatment was significantly lower. So we are working on that process. That's the latest one that we are presently developing, is heat treatment of forgings, castings, those kinds of things. So still work in process. We have a paper that we presented recently, a lot of interest in that, but I don't think we have the full knowledge yet that we can call it a commercially viable process. I will know that only when I start doing my own products heat treatment by this process before I recommend that to anybody else. So yes, because of the speed of heating, the microstructure is extremely fine.
Thank you. Thank you very much. Thank you. And definitely we would like to visit your lab also. There, suppose we got the opportunity.
Yes, you are welcome anytime.
Thank you. Thank you.
Open welcome to anybody.
Thank you.
One more question from Mr. Uddal Hatwar. Is life of grains improved?
No. There's no change in the life. Yes, the life in the sense in an indirect way. If there is no insect in the grain, you will 1 kg of rice will remain 1 kg. If there were insects in that, maybe after 1 year it will become 3/4 of a kg. The grains, the insects would have eaten that. So to that extent, yes.
So Professor Alok Agrawal is asking about that he can suggest his MTech scholars to visit your facility for research work.
Any time, just come. We can talk about certain processes that you have some ideas. We can take up some projects jointly and see what can be done. Yeah.
Kannagi L is asking what type of materials can be used for sustainable manufacturing.
So I spoke about some of the processes. These are all sustainable processes. Baking of grinding wheels, making of steel using only coal instead of coke, and reducing greenhouse gases by 50%. All these are green processes. And now you don't have to use much of fuel. You're using electricity instead of fuels. So there's a lot of advantages, and we can actually do away with coal also by using hydrogen. And as we are moving towards the hydrogen economy, once you start converting water into hydrogen, then the process is, that's why the whole world is moving towards hydrogen steel making. So these processes lend themselves to be green processes.
Sir, I want permission to ask a question.
Yes, of course.
Sir, have you tried infrared heating with instead of microwave?
No, I have not taken that route. We have kindly focused on microwave processing only. I'm sure there are processes that can be done using infrared processes, but we have not focused on that. So I won't be able to answer that.
Thank you, sir.
Thank you, sir. And here to mention, Dr. Rahul Gupta, Chairman of ASM International Pune chapter, also joined this session. We welcome you, Rahul.
Thank you. Thank you, Yogesh.
Thank you. Mr. Udayan Pathak.
I saw Udayan Pathak in the meeting.
Yeah, I am joining from Jamshedpur.
Good. Thank you.
Yeah, I think you should suggest some projects to the students, to the faculty, so they have, they can generate even more ideas.
No, I don't know the capabilities of the institute to know what suggestions I can give. The other way around would be better. You know the capabilities of the institute. You know what I have shown as the capabilities. So if
Okay.
some professors want to come along with their MTech students, we'll definitely welcome them. And we can have a half-day brainstorming session or something as to your interests, how they align with us. So no issue with that.
I think Yogesh, your college should take initiative as a anchor for this initiative, and maybe you can drive them.
Definitely, sir. We will definitely do this with the student chapter of ASM International in our college.
Sir, ask them to
Yeah.
mail us so that we can connect them to us.
If any other institute also is interested, we can help out to reach to Mr. Pradeep Goyal. You can mail us. Yeah. Is there any question? So I think we should conclude today's session.
Great.
And we are thankful to the resource person, Mr. Pradeep Goyal, for his valuable time. All the ASM International Pune chapter members for taking time for us and join this session, and all the delegates who are joining from 6 p.m. For the day one of this ATAL FDP. Thank you very much all. Thank you, sir.
My pleasure. Thank you for inviting me to this event.
Thank
Have a
you,
good
Yogesh.
evening. Right?
Thank you, sir.
Bye-bye.
Bye. Tomorrow, all the participants, tomorrow we will meet at designated time for tomorrow's session. On the WhatsApp group, we will share the details of the session.